Let's get started, guys. Today we're going to explore more on counters and do some finite state machines. So we got two very nice examples. One is going to be the up-down counter, 2-bit. The other one is going to be an elevator. So before we begin, I just want to give you a little introduction on finite state machine. We discussed that on Tuesday, but there are two kinds of machine. One is the Moore machine, the other one is the Mealy machine. The difference between the two is, in the Moore machine, the output is only dependent upon the current state. Okay, so for example, if you remember with the counters that we did, the up counter, the down counter, there was not really an input other than the clock, right? Whereas if you remember when we did an example on vending machine on Tuesday, it was not just the clock but also, you know, what goes in, like a quarter or a bill. Okay, so that would make a Mealy machine. For the most part, what we have been doing is Mealy machine, and we'll continue doing that. Moore machine is usually a subset of a Mealy machine. So if you look at the block diagram here, it's really depending upon the current state. So if it's a counter, and it's an up counter, and the current state is 2, so it's going to go to 3, and then 4, and then 5, and so on. Mealy machine, on the other hand, is determined. The output is determined by the current state and the input. We will use only Mealy machine design to avoid confusion, and Moore machine is just a subset of Mealy machine. Okay. All right. So let's get started with our first example for the day, which is an up-down counter. So it's an up-down counter, 2-bit. Designing FSM, you know what are the steps. So here the inputs are going to be so say we have a button X, okay, and if that button is 0, then that means it's a count up. Okay, if that button is 1, it's a countdown. Okay, so say you are, well, we got 2 bits, so 4, the range is going to be from 0 to 3, correct? So 0, and then 1, 2, and then 3. So if X is 0, so it's going to go from 0 to 1. If the present state is 1, X is 0, it's going to go to 2. Again, if the present state is 2, X is 0, it's going to go to 3. And what's going to happen if it's a 3 and X is 0? So what's going to happen? It's going to go back to 0, correct? Okay, all right. So if the present state is 3, X is 1, so it will start counting down, so it will go to 2. If the present state is 2, count is 1. It's going to go down from 2 to 1. If the present state is 1, X is 1, that means it's going to count down, and it's going to go to 0. And eventually after 0, it's going to go back to 3. Okay, so we got our inputs, we got our outputs, and the transition sequence right here. Let's work on our state diagram. We're going to have 4 states because it's a 4-bit. So you got S0 here, S1 here, S2 here, and S3 here, correct? So let's do for the count up first. So if X is equal to 0, it's going to go to 1. And if the present state is 1, it's going to go to 2 if X is 0 because it's counting up. And similarly over here, if the present state is S2 and X is 0, it's going to go to S3. And then from S3, it's going to go to S0, which is 0. X is equals to 0. Okay. For countdown, so say it's going to be, if the present state is S0, count down, it's going to go to S3, X equals to 1. And similarly, you just finish follow along, finish this. Go from here to here if x is equals to 1, and if the present state is s1, x is 1, it's going to count down to 0. Okay, so x equals to 1. So here's your state diagram. Is there anything that I'm missing here? So remember, you got your states here, which are S0, S1, S2, and S3. Okay, your present states are basically, so Q1, Q0, Q1, Q0, Q1, Q0, Q1, Q0. So those are Q1, Q0. Your next states are going to be Q1. You use the asterisk sign. Q0 here. And then you got your input, which is X. Okay. Let's move on to the next step, which is the state table. Here we also decide what kind of flip-flop we're going to use. Because we used JK last time, let's do D flip-flop. Okay, so again, you got your okay, so we know that in a state table we usually have present states right next to our inputs. So these are your present states, your input, and these are your next states. Okay, if the input is, the present state is 0, 0 and the input is 0, what is going to be the next state? Remember, 0 is up and 1 is down. Okay, so it will go from 0 to 1, so that will be 0, 1. Let's do all the ups first. So 0, 1 will go to 1, 0, 1, 0 will go to 1, 1, and 1, 1 will go to 0, 0. Let's do the downs, which are 1s. 0, 0. Next state will be 1, 1. Good. 0, 1. Next state will be 0. 1, 0. Next state will be 0, 1. And then 1, 1. Next state will be 1, 0. Okay. All right. Obviously, we will have to do K-map, one for each of the next terms, next state terms. Let's do it for Q0 first. So we have 1 here, 1 here, 2 and 3 are zeros, 4 and 5 are 1s, 6 and 7 are zeros. So that's pretty simple. We can make this card right here. And what will be the expression here, folks? Q0 asterisk would be how? You have 0, 0 and 0, 1 here, right? So that will be Q0 bar, correct? Okay. Let's do for this one. So this is 0, this is 1, 3 is 0, 1, 2 is 1, 4 is 1, and 7 is 1. We can't make any pair here, so these will be individual terms. Remember, you got Q1 bar here and Q1 here. Q0 bar dot x, Q0 x, and then Q0 x bar. Okay, so let's drive an expression here. So I'll start with this one. So this will be q1 dot q naught bar dot x bar plus then this one q1 bar dot q naught bar dot x plus this one. So this will be q1 dot q naught dot x plus the last one right here q1 bar q naught dot x bar. Okay, we're gonna have to simplify, apply some Boolean algebra rules and laws here. So say if I take x bar common here between these two terms, so I'll get q1 dot q naught bar plus q1 bar dot q naught plus, and then I'll take x common between these two terms, so I get x here q1 bar dot q naught bar plus q1 dot q naught. Okay, all right. What kind of a gate is this, folks? Exclusive OR, right? Okay. And what about this one? XNOR. Okay. And how about this one right here, the whole thing? This whole thing makes what? Exclusive OR, right? So I actually can write the expression as x exclusive ORing with q1 exclusive ORing with q naught. Okay, that's the expression. Once we have these expressions, our next and the last step is to implement, come up with a sequential circuit design. I'll put my equations right here. Okay, now you have to remember this. The next term for a D flip-flop is equivalent to what? When the clock is 1. It's equal to D, right? Correct? Remember, when you have clock set to high, your next term is always going to be equal to D because we're using D flip-flop. Correct? If it was J and K, would have been different. So to D, remember that. So say I have because it's a 2-bit up and down counter, so I need 2 D flip-flops. So say this is D, this is D, this is Q1, this is Q naught, this is Q1 bar, this is Q naught bar. Obviously this is going to be the clock here. Looks like it's positive edge triggered. Okay, so where is going to be my next term, next state here on the D flip-flop? And where is going to be my present state? Monday, lazy day, right? So yeah, come on. The next state is going to be right here, correct? Right? Next state right here, next state right here, and the present state are going to be Q1 and Q naught, correct? Right? And that's how we had over here as well. Q1, Q naught, those makes present states, right? Okay, all right. We'll start with Q1. So I'm gonna pull my gun here, so I can make that exclusive OR gate here. Okay, all right. So because this was Q1, so I had to connect the output to this D right here, and then I got X, which is one of the outputs, inputs, and then I have Q1 and Q0. So actually take so just making connection, wiring them up. This goes here, this is connected to this. This is my Q1, this is my Q0. Okay. So this is my Q1 and this is my Q0 right here. Okay, so I've taken care of this expression right here. Now I need to get Q0 asterisk, which is Q0 bar. Okay, so Q0 bar is right here, correct? So I can just feed that back into this D flip-flop, correct? So I'll use a different marker. So this goes here. This goes right here. And then just wire them up. There you go. Okay, so this is your Q0 bar here. So all the connections been made. Remember, this is your This is your Q1, right? Q1, and this is your Q0. So your Q0. What is this right here, guys? This is your Q1 asterisk next state, correct? And this is your Q0, the next term. Okay, so say you have so you got present state is 0. Okay, 0 0. That would mean you have 0 here, and then you have 0 here. We're trying to implement and verifying our logic here. What do you want to choose your input? Count up. So that would be x equals to 0 was up, right? And then 1 was down. That's how we had, right? 0 is count up, 1 is count down. Okay. All right. So I'm going to choose x equals to 0. So what should be the next state? Presently it's 0 0. Next state should be 0 1. Okay, let's do that. What is Q0 here? 0. Q1? 0. Okay. 0 going through an exclusive OR gate. What would that be? 0, right? So you get 0 here. Clock comes in. This is a positive edge triggered clock. What would be the output here? 0, correct? The output is 0 here. All right. What about here? This flip-flop right here. Q0 asterisk is connected to Q0 bar. Initially it was 0, which means Q0 bar is 1. 1 is being fed here. Clock comes in. The output changes from 0 to 1. So now you have 1 here and you have 0 here. So it went from 0 0 to 0 1. Count up. That is how it was supposed to be, right? You want to try one more combination? Okay. Say you initially, so look at the black. Initially we had 0 0. We had x 0, so it was counting up. Let's change the x to maybe 1. So the next state would be what now? It's counting down. So it will go from 0 0 to 1 1. Okay, all right. initially Q1 and Q0 0 again. So 1 0 0 going through an exclusive OR gate, what would be the output? 1. Okay, so we get 1 here. The clock comes in. This data bit at the input of the D flip-flop will be loaded into this flip-flop. So this will be 1, correct? Okay, all right. Initially, this was 0. So the Q0 bar is going to be 1, which is feeded into this flip-flop. Clock comes in again, and the output will be loaded into this flip-flop, which will be 1. So it went from 0 0 to 1 1. Initially it was 0, right? So here X was 1, here X was 0. So here it went up, here it went down. Okay. So this is your 2-bit up-down counter. Same thing, you can implement this into 3-bit, 4-bit, or 8-bit. Okay. Do you see anything different in this sequential circuit design compared to what we've done in the past? Anything different? There's one thing different actually. So, yes. They are connected. What are connected? See, if you look at the clock right here, you just have one clock, right? We got one clock, and that is fed into both flip-flops. So this is a synchronous, correct? It's not asynchronous. It's not like the output of one flip-flop is connected to the clock of the next. Okay, so you see those changes and the counter at the same time. So it's a lot more faster. Okay, right? That was example 1. Shall we move on to the next example, folks? Is everyone following me? Okay. We're really low on energy today. What's going on? Okay. Our next example is an elevator. So the elevator can be at 2 floors, ground or first. There's one button that controls the elevator, and it has 2 values, up or down. I'm thinking it's maybe something like this. So maybe it's something like this. This is your, okay, then it has something like this. Okay. Of course, this is your up and this is your down. Okay. Also, there are 2 lights in the elevator that indicate the current floor. Red for ground and green for first floor. Okay. So say they have something like this. Floor 0. This is the ground floor. First floor. So here is an LED. Well, I got red color, so red LED here, and then green LED here. These are LEDs, okay? And this is the floor. Okay, at each time step, what it really means is every clock cycle, the controller checks the current floor and the current input, changes floors and lights in the obvious way. Okay, so moving on to the steps for making a sequential circuit or a finite state machine. First comes up is a state diagram. How many states are we going to have here? Why do we have 2 states here? Yes, David.
It can either be on the floor, it can either be on the ground or the first floor.
Correct. There are only 2 floors. Let's say if it's a 15 floor, so you'll have 15 states. Okay. So this is your ground floor. Okay. Remember, this is going to be red. Here's your first floor. And this is supposed to be green. Okay, all right. So say 0 here is down and 1 is up. Okay, So you are at the first floor, not the first floor, ground floor. Input is 0. What should happen? It should stay where it is, correct? Right? So, okay, this is 0. And if you are the ground floor, input is 1, or this thing right here. So you go to the first floor. If you're at the first floor, you press the first floor button. This button right here, you stay here. 0, and then this will take you right here. Okay, so this is going to be, actually this is going to be 1, right? And this is going to be 0, and this was 1, correct? Alright, so 0, 1, 1 here, and then we got 0. So we got our state diagram. We're going to move on to our state characteristic table. And again, you know, in a state table, we put our input state, present state, and our input right next to each other. So for possibilities 0, 0, 0, 1, 1, 0, and then 1, 1. Okay. So if the present state is 0, which is a ground floor, so this is 0, this is 1. The input is 0. What should be the next state, folks? 0, okay. Here, the next state is going to be 1. What about here? Input is, present state is 1, input is 0. 0. And then, again, you're at the first floor, you press 1, the output is going to be, you're going to stay there, correct? Okay, what about the red lights and green lights? I got 2 extra columns. Remember, if you're at the ground floor, we need to have red lights lit up, and if you're at the first floor, we need to have green lights lit up. How would we make a truth table for that? Those 2 columns. What do we look at? Come on. Not you, someone else. So we can just look at our present states, right? If the present state is ground floor, what should lit up? Red light, correct? So that would be this one, right? Because these 2 are 0, correct? And this will be 0, 0. And then if you are at the first floor, you should have green light lit up. 0, 0, correct? So we got our state table ready. We're now going to move on to our next step in the sequential circuit design, which is the coming up with the Boolean expression. Okay, so technically we should be having 3 K-maps here, one for the next state, one for red LED light, and one for the green light. Let's do this one for Qn plus 1. Okay, so remember you got your Qn here, and you got your X here, 0, 1, 0, 1. Okay, this is 1 and, 0, 1, 2 is 0, 2 is 0, and then we have 3, which is 1. Okay, alright, that's pretty simple. We can go with this pair right here. What is going to be the expression here, folks? Yes, X. Pretty simple, right? X. Okay. Okay. And then we can do another 2 K-maps and get expression for a red light and green light. But since if you actually look at the expressions, I'll show you how you can get it done. So again, we are using a D flip-flop here. Okay. And then we know that next state, when clock is high, is equals to D. So what should be feeding into this D input right here? It will be X, correct? Okay. Remember, this is your next state. And this is your present state. Okay, this is going to be your clock. Looks like it's positive edge triggered. Okay, all right. How about the red light and green light? Say present state is 0. What light should turn on? Yes, guys. Yes. Red light. Okay. So we're gonna have a red light here. Okay. But because we have 0 here, somehow we have to find a way to invert this logic to turn the LED on, correct? So it has to go through a inverter, correct? Go. Okay, and then you go to, obviously you're going to have the resistor 2.2K, or does anyone know how much red light needs in order to light up? Anybody who's taking 2019? No? It's 1.8. Okay, all right, and we know mostly we give 3.3 and 5 volts, so it's going to work. So you just need a resistor in series with that. Okay, what about the green light? Say it again. Say it again. 2.1 what? Oh, for the red LED light? For the green? Green, I think 2.1, yeah. Green is 2.1, which will still work because we are giving 3.3 or 5 volts, okay? So for the green, how should I wire it up? So say if the present state is 0, the green light is supposed to stay off, right? So I'll just wire it with the green light. Now, I did it this way because I just wanted to do it a little differently. But again, you can do the K-map, come up with an expression, and wire them up. Okay, let's now verify logic. Okay, so present state is 0. What do you want to choose your input X as? 1? You want to do 1? Okay. So 1 is the input. The person is at a ground floor. So if he presses 1, remember this right here, the elevator is supposed to go from the ground floor to the first floor. So the clock comes in. Okay, this 1 bit will be stored in this flip-flop, and the output will change from 0 to 1. Now notice here, as the logic goes from 0 to 1, red LED light is going to go off and your green light is going to turn on, correct? Okay, so this is just a simple elevator, but you, like I said, you can build upon it and make it a little more advanced and more complex. These were the 2 examples. We started off this course with transistors. We learned about how MOSFET could be used to create logic gates, and then using those logic gates we actually made logic functions, and those functions we then use them to create flip-flops. We then use our flip-flops to create counters and sequencers. Sequencers we'll do tomorrow, okay? And once we have those counters and sequencers, we can actually put them together to make microprocessors that can make smart decisions for us. And then we can put microprocessor to make computers. So we are actually to the very bottom part of it. So that's what we are going to do this week, okay? I'll see you guys tomorrow, okay?